us to welcome our speaker. Yes.
Hello, hi. So today we will present our talk on multi-cluster GPU allocation for AI research, AI workloads. So I am Ritik and I work at, as a platform advocate at Loft Labs, and I'm a CNCF ambassador, Google Scholar. Over to you, to my co-speaker.
Hi everyone, I'm Shvai. I'm a developer experience engineer at Couchbase. I'm also a CNCF ambassador, and I've been a contributor and maintainer for a lot of different open source machine learning projects like TensorFlow, Kubeflow, and also GitOps right now. So, of course, we have seen in the last 3 to 4 years that as the number of use cases for LLMs have grown, we have also seen this that in just the past 15 to 20 years, we have gone from really basic uh, natural language models, so having very basic neural network architecture, to now having millions of parameters with these state-of-the-art large language models. So keeping in context of open source models, we have also seen that OpenAI just recently launched their GPT OSS models, which are available for anyone to use. So in terms of the growing architecture and the complex architecture of these large language models, the complexity of how we basically have to handle these particular models has also increased. So which means that as these models are becoming better day by day, the complexity of having to train them also increases, which means that there will be a bigger need for more efficient way for being able to leverage GPUs, because GPUs are very expensive to run, and modern day LLMs require you to have a cluster of large number of GPUs, and if you're running them in an unoptimized manner, it will basically increase the total cost associated with running these models. And primarily, if you are doing a lot of research, that is basically the phase even before inference. So of course, inference itself requires a lot of GPU power, but the training part of these models requires even more compute. So for research institutes or financial institutes or companies which are basically training their own large language models, or maybe they are fine tuning their large language models and require a lot of GPUs, we need to be able to do that efficiently. And today we are going to be talking about how you handle all of that. Now, as we mentioned that when you are increasing the complexity of these large language models, you want to be able to design your GPU infrastructure that can scale, that also supports batch processing, because if you're running multiple workloads at the same time, we need that to be handled. And we need to design a proper MLOps pipeline that can not only give you a proper GPU cluster for training, but also in the future for inference as well. And you want to have proper telemetry required as well, so that you can keep a note of the growing cost that will be associated with running these GPU nodes. And we've already seen a lot of different companies contributing to this entire open source spec. So of course, we have a lot of large language models, but there are a lot of companies that are also working collaboratively together to be able to make the GPU inferencing more accessible. There are frameworks that we'll talk about today, which are being contributed by companies like Hugging Face, OpenAI, Bloomberg, Nvidia, and of course, to power all of it together with deployment of these GPUs on Kubernetes. So just to kind of give an example, OpenAI, of course, they are one of the largest companies in the space for, being able to run GPU workloads. They shared that they have been able to scale up their Kubernetes clusters to more than 7,500 nodes, which has enabled them to be able to do the training and inference for some of their largest large language models like GPT-3 and DALI. And of course, all of that, which means that if you look at GPT-5, which is one of the largest models that was just launched a couple of days ago, or GPT OSS, they have all been trained by using a large number of GPU nodes on Kubernetes that is running inside of OpenAI's cluster. And it's not just them. If you also know about XAI, all of their different models like Grok 1 to Grok 4 have all been trained on Kubernetes by using GPU clusters. Now, a typical AI workload lifecycle looks like this: that you develop, you train and deploy and also serve. So these are the generally your machine learning pipeline steps. All of them are managed with the help of Kubernetes. So right from the time when you have just your raw model weights and you're actually training them to adjust the model weights, all of them is happening on top of Kubernetes, which also means that we basically need to find a way that the process in which we are using the GPU weights are efficiently being used on top of Kubernetes. And that is why we have seen a huge trend of being able to bring GPUs to bare metal Kubernetes for AML, because of course, if companies are having their own infrastructure, they're not relying on any cloud provider, we need to find a way of being able to like leverage these GPUs in an efficient manner. And we'll understand the reason behind that. So generally, if we understand, okay, LLMs require GPUs, and we are using these large number of nodes in Kubernetes for companies like OpenAI. So how do we integrate a GPU with the help of Kubernetes? So there are primarily these two different level of components. One is the host level components, and then we have the Kubernetes specific component. So the host level components are basically the things that are required on the GPU provider side of things. So that is why you'll see that we have things like the NVIDIA container toolkit and the NVIDIA GPU driver. So these are being provided by the GPU provider themselves. So these are open source by NVIDIA. And then we need to have some components on Kubernetes level so that the pods that are running inside of your Kubernetes cluster can basically identify when there is a GPU resource, because the GPU feature discovery and the K8s device plugin, they will be able to identify when a GPU resource is available for you to use, and you will be able to then identify that, and the pod will be able to access that GPU that has been made available specifically for Kubernetes. And let's also understand that as an example. So here you can see that when it comes to integrating a GPU with NVIDIA, like let's say an NVIDIA GPU with Kubernetes across your different nodes. So here you can see a YAML spec for your Kubernetes cluster, where in the container you can see that we have provided the image as NVIDIA, and we have provided two number of GPUs. So this means that there'll be two GPUs available for your pods inside of your cluster to be able to be leveraged. And primarily this is what we had mentioned earlier. So this is the NVIDIA GPU operator. This is something that's coming from NVIDIA, which allows you to not only manage the lifecycle of your cluster, of your GPU running inside of your Kubernetes cluster. And this is something that comes from the host level component, which will be leveraged by the Kubernetes, which basically interacts with the Kubernetes device plugin as well, to be able to get access from the Kubernetes pod that you're running it with. And this enables the communication between the pod and your GPU. But now there are a few issues with running your GPUs within Kubernetes, and these are primarily because of the fact that yes, there are certain limitations within native Kubernetes itself, and also the sequential nature of these large language models. So the first one is that generally serving LLMs is very expensive, and that basically comes down to the fact that there is a sequential nature of LLM inference, and which makes your processing extremely slow, right? Or it takes a lot of time. And considering that there's nothing built in within Kubernetes that can help solve this, so this can basically lead to a lot of time getting wasted. For example, one NVIDIA A100 can only process less than one request per second. So imagining if you are having so many different requests, it basically adds up and can basically like lead to a lot of unwanted cost as well. And way that we overcome this is that you can use open source projects like VLLM, which enables for much more improved batch requests taking place, and it also uses something called as paged attention, which enables you to have much more capable way of being able to batch your request, which is not natively provided with Kubernetes. An additional thing that is there is that there is a lot of idle time. So what this means is, imagine that you have, let's say, 2 or 3 different GPU nodes. Now, not every single model actually requires you to have access to a single GPU all the time, which means that if you have a smaller model, like let's say if you predate before LLMs to a simple MobileNet model, it will actually not end up using your entire GPU for training or for inference, which means that if you have, let's say, only 40% of your entire GPU being utilized, there is the 60% that's just sitting idle, but you're still paying cost for that remaining 60%. And similarly, like if you have a combination of multiple GPUs and only some portion of those GPUs are being used, that means majority of your GPU is being underutilized, and that's just again unwanted costs that you could basically cover up by using much more efficient way, or essentially not allowing your GPU to go unwasted. And we'll basically explore these techniques that my co-presenter Ritik will talk about, where you can basically enable you to use your GPUs in its complete fruition and not having to waste your GPUs where there's some idle. So we'll explore techniques where the GPU workloads are not just sitting idle, and how you can leverage techniques to reduce that. So over to you, Ritik.
So, the thing we want to focus on is like the divide in the GPU. By default, it is not supported, but there are a couple of things you can do that to happen. First is requesting a fraction of the GPU. So this is one of the most common approaches. And then you have approaches like time slicing, in which there is a sequential order. And whenever a process or a pod or a system requires a GPU, you skew it sequentially in the time manner. So as you see, we are using it over here. And then there is MPS as well. So where you allow multiple CUDA processes to share context and use it. So this is how you do that in the form of Kubernetes pod aspect. So those are the most common ones. And moving forward, if you want to understand how things add up, we need to understand how the GPU operator pod and Kubernetes node happens. So suppose you have 3 nodes and each of them have GPU, like in the green diagram. And normally one of your pod can request 1 GPU, as we have seen before. So over here. So the problem with this is like your GPUs are blocked whenever there is a request going through, even if you have everything enabled. So then you can have a lot of sharding and all those things for your GPUs. But again, there are new ways by which you can do this. And there is hardware ways, like where you can have GPU sharding. And there are software ways like the Kai scheduler. So with Kai scheduler, it's a scheduler from NVIDIA which helps you to help and allocate GPU for your research and inference. For example, if there is a solid 1 unit of GPU, you can have a fraction GPU for your fraction use cases. So one of your GPU has been broken down into 2 parts, for example, and one part is being used by your inference and other part is used by your training. So that can be possible. Apart from that, the Kai scheduler is there for helping you to streamline scaling for AI ML workloads, and it helps you to focus on dynamic GPU allocation. So using the full length of your GPU without performance issues. So whenever we have a Kai scheduler, the architecture kind of changes over there. So how it changes is like your Kai scheduler is the one managing the scheduling of your GPUs between different pods. So there can be a scenario like a GPU is being served by 3 pods instead of the other scenario where one is linked with one another. And then there are a few more problems whenever you deal with building new things. Then the problem is about tenancy, automation, and isolation. So for example, here you can see that you have 2 GPU pools and 2 clusters. So each of the tenants are using Kai scheduler to consume the GPU, but there is problem with the utilization. Red means how much utilization is there, and green means how much is available in both of the diagrams. So for example, you are building custom resources for your new AI workloads and research. So the traditional problem with Kubernetes and namespace isolation is that you can't do that because the problem exists in how cluster level objects are isolated. But when you have two tenants, you can do that. But the problem is how utilization is happening. So if you see on the right side of the diagram, the utilization is very low because there is a lot of GPU available, which is not good because GPUs are expensive, and when you are wasting the resources, that is not good. But on the other side, where you are using 80% of your GPU, that is also not a good sign because you are overutilizing your GPU and there might be performance degradation. So a native approach to this can be something like combining all of them together, all of your GPU nodes to a single cluster, so that if you have tenants, couple of them, and your Kai scheduler is managing all of the resources and all of the GPU sharing. But the problem again exists on the cluster level because of CRDs. Suppose you have a lot of CRDs on your different objects. There is an issue of how isolation is working with cluster level objects. So here something like vCluster can come into the picture. So vCluster is an open source tool, and what it does is like it helps you to create virtual clusters on top of your Kubernetes cluster. So you can have a whole node pool of GPUs over there on your host, and whenever a research team, a research developer requires a GPU, they can create a virtual cluster with help of vCluster, and then they can consume a fraction of the GPU with scheduling like Kai scheduling or others, while having isolation at the host. So each of your teams can have a specific virtual cluster with specific GPU sharing enabled. If you want to look into a diagrammatic way, this is something like this. So tenants are your individual research unit or researchers. So whenever they require GPU, they can create a virtual cluster, and for different tenants, there can be different virtual cluster. And the advantage is like you get fully isolated block like your normal Kubernetes cluster. And then with help of these scheduling algorithms, you can consume GPUs from all across the node pool in a way that is efficient, not over optimized, but good utilization. And again, for example, there are a lot of use cases where you need more powerful GPUs for more powerful models. Suppose you are doing a very high powerful model with a lot of parameters, then you will require a more powerful GPU. But suppose you are just doing a mobile model, then the requirement is not that high. So you can also divide the GPUs in form of node pools and use labels and selectors, which is a Kubernetes object, to assign the specific GPU to your specific pod, so that there is complete utilization as well as better use of them. Apart from that, you have the option generally to overall create new clusters at the whole, so you have more utilization overall, while focusing on the most important part is like the training and the inference part. So when you talk about all those things, what is the main goal is like whenever you use something like virtual cluster with help of Kai scheduler or normal scheduling as well, so you get fully isolated units including CRDs for your workloads. So if you are sharing a cluster across different teams, there might be a problem where you are building new CRDs or something like that and new operators, but as those are cluster level objects, those fail because you can't have the similar version again and again. So when you create virtual isolated units for your cluster and all those things, so you get this like the fully isolated unit while also getting the benefit of sharing GPUs. And then there is one more part is you also save on cost because you don't need to pay for your control planes again. Because for example, if you're running a EKS cluster or something, you pay $60 per month for that control plane unit. So you abstract away the cost. But again, the other cost you are saving is saving on underutilization of GPUs. So GPUs are one of the most expensive hardwares you use for your research. So if you're using it in an optimal way, you are saving on cost and improving your efficiency overall. So yeah, and if you want, should I?
And just to kind of give a breakdown, we'll also just like to show you the Kai scheduler with vCluster. So we can just go over the docs once. All right. Yeah. So here you can see that this is like a guide that you can also explore, where you can see that we have configured our vCluster configuration for Kai scheduler. And first we just go ahead and as you know, it was shared by Ritik that you can create two different vClusters or as many number of vClusters as you want, and this allows you for much better resource isolation. So here you can see that we are basically creating a new vCluster with the Kai scheduler configuration baked in, or if you have an existing vCluster, you could also manage that. And as we saw that basically what exactly is a Kai scheduler? So it's a open source scheduler that's helping you to enable things such as dynamic resource allocation of the GPUs. So in this case, here's an example of just a CPU only pod which is running Kai scheduler, but we are more interested in the GPU pod. So here you can see that when we are enabling it for that particular pod, we are also adding things such as the NVIDIA SMI, which enables you to leverage the GPU for being able to get access to that GPU node. And then we have given the specific resource limits over here for our GPU. And then of course, as we know that we can also enable fractional GPU access, so that this enables you to be able to share your GPU nodes across multiple workloads. So here you can see that we are enabling 0.5, which will be request only half a GPU in case your ML workload does not require you to have a full GPU access, so that the rest of your half GPU is still available for other machine learning process to be able to be used. And so that's where you can manage all of that. And then once you have configured everything, you can take a look at your pods and the scheduler. And finally, that's where you can see that how everything basically works behind the scenes, where you can basically group related pods for optimal scheduling of how these particular GPUs are being used. And you can basically like set all of these limitations as well. And I wanted to also just kind of cover some of the other aspects of Kai scheduler. So I'll just go to the GitHub repository because that's one of the more interesting aspects of Kai scheduler, where you can see some of the benefits that we have basically described. So that's the open source project from NVIDIA, right? And here are some of the core aspects that we basically like covered today. So things such as dynamic resource allocation, which basically means that whatever resources that you need from a Kubernetes point of view, right? They are things that you can basically set up. And then you also can enable batch scheduling, which means that some of the things that we spoke about, VLLM, are also being provided by Kai scheduler itself. So that's another one. And then of course, as we mentioned, that you have built-in GPU sharing. Now, finally, like one of the other aspects that we wanted to also cover was dynamic resource allocation, because that is something that we spoke about around as being a native feature. So within Kubernetes, this is a new feature that's coming in or has been in beta for a while, and this essentially again is something that will hopefully get released in public preview soon enough. But this is where we have mentioned that it's the feature that lets you to request and share resources among the pods, and this is what you're basically getting baked in when you're using NVIDIA Kai scheduler inside of your Kubernetes cluster. So you don't have to set up DRA automatically. Like it will use the beta version of the DRA to enable sharing of the GPU resources across the different pods. So those were some of the main things that we covered in our talk today. Of course, with vCluster, you get even more isolation, and you don't have to manage that on your own with built-in Kubernetes. So that is where how you can also interact with the vCluster community. So there is a community Slack for the open source project. And anything else, Ritik?
No,
all right. So yeah, we'll be open to questions now. Thank you so much.